Move on to our next group of speakers from Yale in the US, the Quantum Institute, and several other affiliations as well. It's a team of 4 people led by Florian Carle. Then we have Spencer Topel, Luke Burkhart, and Kyle Serniak. So thank you guys for taking the time to prepare this presentation. And we'll hand you over to who is going to start, Carl?
Yes, I'm Florian. Start.
Hi, Florian. Thank you.
Hi.
The floor is yours.
Thank you for having us. We're delighted to be here to present our work of quantum sound. This is a partnership with the Yale Quantum Institute and Spencer Topel, who was our artist in residence in 2019, and he works now on his company at Physical Synthesis. So I want to go over like a few very quickly. I don't think it's.
Maybe it's play for the top 2 also the timer.
There you go. Sorry for that. So I think we more or less know all about the quantum states, but I want to really show how to represent quantum states. So you know that a classical bit can be 0 or 1. So if you excite them, and then a quantum bit is of course the combination of all of them. And so you have multiple ways to present it. You can use the Bloch sphere, or you use the sphere and the polar angle to represent this, or you can do the Wagner distribution, and then you have this plot. And so basically, you can see on the screen. Excuse me. You can see on the screens here. And so the screens are. So the camera.
They can see it there too.
Yeah. So the cameras are here, and so you can you see like the distraction of this thing. And so the interesting thing, and that's what we use in our residency, is that we want to use the wave collapse, like the decoherence of the quantum states, to make the system like unstable until you drop them into the system. So, for example, the observer effect is here. You have your qubits in internal states, in superposition states, and then you observe something, or the environment is giving an interaction, and then you land into one state. And so you can see that on the graph over there, where you can see the fringe are here. So you put it in a superposition of states, and then the fringe disappear over time. And so this is the observer effect. And so this is the core of what we used for the synthesizer. You can really use projective measurements as a control voltage for your synthesizer. So that's basically the theory. And so to go to the practice, and what we use is we want to harness the power of quantum physics at the atomic scale and the complexity of integrated circuits. So basically, if you take one atom, you have electron rotating around at a very small scales, and it's really hard to do because you have to isolate one single atom. And then, so what we've decided to do, and that's the approach that the researchers at the Yale Quantum Institute are doing, is they want to harvest the complexity of integrated circuits, which is basically a technology that that's really mature and that we can work. And so instead of measuring the voltage of one atom, we have 10 to the power 12 electron moving and sinking together. You can see on this representation of this thing at the scale of like 0.1 to 1 millimeter. And so this is basically what we use. We use artificial atoms in the labs, which are called transmon qubits. So basically you have 2 islands, and then you use a capacitance and a Josephson inductance in parallel. And so basically people who've worked in the electrical engineering knows this system, because it's basically an LC oscillator. You have a conductance and a capacitor, a nonlinear inductor and a capacitor, and that's basically a circuit. So in practice, this is what a transmon look like. You have on this integrated circuit, we have a sapphire substrate where we have the capacitance and the Josephson. So the capacitance is here. It's this blue line that you see on this thing that we use. So it's a very small scale. It's 300 micrometers. And then in the middle that you see, you have here the Josephson junction, which is 2 pieces of aluminum that have been etched onto a substrate. And then you have a thin coat, a thin bridge of oxide of aluminum. And this is where all the electron will tunnel through. And so you have basically your system. So yeah, and so in practice, we create these very elaborated circuit QEDs. So it's basically an all-electric control and measurement chip that you can use in your computers. And so you use microwave lines to control all of the system. And so on that chip, you can see that the transmitter here is on 4 spots on the chip. And so we have this chip, this particular chip that has been produced basically like you do for semiconductors, but you just replace the semiconductor by superconductors. And so we have 4 of these, and you can control all of these things. And this is the most promising technology for the scalability of quantum computing. And that technology has been developed since the early 2000s at Yale. And so all of this is the timeline of all the innovation in that space of superconductive qubits. And so that technology has been used and adopted majorly by all the tech giants, IBM, Google, Microsoft, and a lot of groups in the US and the world are using that technology to develop the computer. So if you, in practice, you want to see like how it works. And so basically you have this, so all the transmitters that I've shown you are this little, it looks like a little glass on the screen at the middle of the cavity. It's an aluminum cavity. And so you have this chip in it. So when you zoom in, you can see the scanning electron micrograph that you have of the bridge. And so basically this is one of these things that we use, and all of that goes inside the dilution fridges. So to really take the power of all the superconductive devices, you need to cool them down at almost absolute zero. So the whole cavity goes deep inside the dilution fridge, which is basically a Russian doll nested into, it's a big fridge nested into another big fridge. And so at that point, you're able to reach a temperature of 0.1 millikelvin. So almost, it's colder than outer space. So it's really fun to have these big machines in our labs that students are working next to that are extremely cold. So this is the technology of quantum computers using the dilution fridges. And so we use these computers so this is an open version. You can see the CAN version is when they're running, when they're cold, and when they open, they look at this. They look like these copper machines where you have all these stages of cooling down. And so we control these with analog input and output. So we have classical computers running this machine and oscilloscope. And this is basically the way most of the quantum computers accessible on the clouds works. And we have at Yale a latency of about 200 nanoseconds. So really good for that. And so we're all talking about that because it's a very complex system. But the reason why we're here today is because I want to talk about the Artist in Residence program. You, in the audience, you're in this rare crowd of people very interested in quantum computing, but it's really hard to talk to quantum physics to the general public because it seems to be a very difficult topic. And so we've developed this program at Yale of bringing an artist for a year-long residency to work with our researchers, students, professor, and develop some artwork. So we started this program in 2019, where we welcome Martha Lewis, who is a visual artist. And she installed in our space just in front of us here this big human scale version of the dilution fridges. And then the reason we're here is because Spencer Topel is a sound artist, and he joined us in 2019 for a year-long residency, and we developed quantum sounds, which is using the quantum computers as a system, as a synthesizer to create a piece of noise music. And so we'll have plenty of examples to hear the songs. And our new artist this year is Paul Miller, aka DJ Spooky. And so he's gonna work on multimedia art. And so all of this thing is to do a program to really engage the audience and really encourage people to be interested in this field. But yeah, let's focus on Spencer Topel residency, and I'll let you the floor for that.
All right, thank you, Florian. So in 2019, it was actually, I think 2018, I got an email from you, or maybe was it 2000? Yes, in 2018, I got an email from Florian, and I thought it was a joke, because, he's like, hey, I'm from Yale, we're working with quantum systems, and we want to invite artists. And so I sort of ignored it, thinking that maybe, it wasn't real. And then he gave me a phone call and said, yeah, we're really serious about doing this, and can you come down and do a talk? So at the time, I was developing the product for my company now, Physical Synthesis, called Cicada. That was born out of research into electromechanical systems, which led to our patent on the subject that involves nonlinear signal mixing in physical system. in physical systems. And when I came to Yale and I saw what they were doing with the dilution fridges, which is largely signal mixing in these kind of very specialized systems, I realized that there was a huge musical potential. And so following the talk, one of the things I wanted to do right away was say, can we use these dilution fridges, these superconducting systems, as musical instruments if possible? And how would we go about doing that so that we could really understand the connection between like we said, like we've been talking about in this whole symposium, data and its result in music and sound. Two individuals sort of came forward after the talk, Carle Serniak and Burkhart. And Kyle's shown here on the right here with the tattoos. He is a wonderful, gifted physicist who works now at Lincoln Laboratory, MIT. And he's also an amateur musician. He played in bands. So he was excited to kind of blend the two together, and he'd been thinking about that for a while. So over the course, I think, of the first 3 months of the residency, we really explored different projects. One is here shown here by Yuan Chu. We looked at, she's an expert in transduction, and in particular, how to prolong the information of these qubits by transducing that energy to other forms, say light or sound. And she and a lab in Colorado were the first to produce the first, observable isolated phonon or sound atom. So part of one little kind of side project we did was looking at how we could kind of model that in a classical system. And so you can see here, there's a big glass plate, and we put a small kind of piezo actuator on it, just a disc, and it just created a small ping. And then we recorded that resonance, and it doesn't sound like much. It's just a bleep. Do we present original sound with our present?
Yeah.
Okay. So we basically have this small pulse, and what we found when we looked at the two waveforms together is that they strongly resembled what they saw inside the fridges, that you had an extended resonance as a result of the glass plate. It was very similar to the device they used in the fridge. Another angle we took was, can we use data from the fridges, but also can we synthesize signals into the fridge to generate new behaviors? So with the two projects we worked on, let's see. So at first we analyzed and looked at the audible raw signals. I'm sure some of you have heard what this sounds like. It's just kind of correlated noise. Doesn't sound like much. And then, let's see, how do we stop it? And then, yeah, so then what we did was we looked at how we can use these signals slow down, sometimes 10, 50, 1,000 times, to get control signals out of them. And I'm going to show you some of the processes we went to do that. And finally, I didn't want to leave the scientists out of the artistic process. I wanted to include them in as performers because I felt, one, I like collaborative performances, and two, I knew they would be more invested in the project and maybe the outcomes, particularly around sonification and synthesis. So to start with, we were interested in, with Kyle, he was working on a set of experiments with this JPC fridge. These were specifically examining non-equilibrium and quasi-particles in superconducting qubits. And what that means is, effectively, there's a set of free electrons, positive photons that exist in the system, and by changing some of their circuitry, they were interested in measuring those behaviors. And what this kind of led us to, for the purpose of our project, was an ability to determine effectively 4 states. So we had in addition to like what you call like a ground state, excited state, we also had a kind of odd and even state that we could measure that was part of his research. So I'm not going to go into too much of that just for time's sake, but what this led to was kind of this breakdown of information. Effectively what you see are kind of different levels of the information here. And while it's represented as a signal, these are instantaneous measurement jumps. They're effectively, they're not a continuous signal, but they're just, they're measurements in time that show it's either kind of an instantaneous leap from one state to another. So at one end, you have kind of the what you might call your typical ground state here, and then you have your even state. So it's kind of excited state. And then you have your excited even state and your excited odd state. So those ended up being a way, you'll hear kind of these 4-note melodies like I showed you in the example before. That becomes a kind of tool for the synthesis. In the case of Luke, we explored kind of two different methods, two different synthesis methods. One involving error detection networking between two qubits. And so what they were interested in doing was having one transmon kind of read the other one. And so based on that error detection, it would correct the error or not correct the error. So we kind of, from that, you kind of, and here's the physical example of the hardware. So from this, we kind of came up with a scheme for sort of good following and bad following. So if you think of like a violin teacher playing with their student, a good following would be that the student plays exactly with the teacher. And then a kind of, if the student isn't quite following, then they don't match. And I can show an example of that real quick here. I think I can just jump out, right?
Escape.
Escape, and then
put your Ableton
okay.
Onto the
yeah.
screen.
So and then
the second screen.
Where's that? Go ahead. Show that real quick. I don't know. Okay. There we go. So here we go. So in this case, we had kind of the data here. If you want to look at that here, it's you know, again, these are just kind of converted to audio signals from the measurements. But if we go back to this is a kind of Max for Live patch that uses Gen to do the kind of category selection of the oscillator frequencies. So in the case of good follower, it's going to be kind of tricky. So in this kind of scenario, you have following of the signals that's pretty evenly matched. However, when the measuring is weak, is kind of the connection is weaker, you end up getting bad following. Still correlated, but not as much. And then finally, it's now decorrelated. So it's just going to be kind of sounds somewhat similar, but not played together. So again, good behavior. Okay, so what I think is pretty exciting about this example is, and then I have to switch back.
Yeah,
let's
keep going all around.
What's exciting about this to me is that, you know, to get a similar effect in a classical system, you have to kind of add a lot of extra steps to this. You have to add either some sort of randomization selection, or if you're an electrical system, you're doing transistor selection. So yeah, you have this notion of like good following. Oops, let's go back. Good following, and then sort of bad following. So yeah, those were kind of our first two, our primary synthesizers we made for this project. Let me give you just a quick tutorial breakdown of what the thinking was to construct these two and the third version of this. And the thinking is that effectively the quantum data is downsampled and converted into audio rate signal. And the reason the audio rate signals are interesting or useful is that you can apply phase modulation through one of the signal paths so that you can actually hear the quantum fluctuations. Those quantum fluctuations are these naturally occurring kind of wobbles and vibratos that happen in these systems. And I felt like it was kind of, if we're going to go the sonification route, we'd lose that information if we were just simply selecting states. The second part is logical gating, and we've seen a lot of that in the talk so far, that effectively you want a way that you can select, you know, ground state and excited state, for example, in your system, and then discern some sort of logic from it. So in our system, we used Max for Live with, at first we tried the native library with the gate signal object, and it had all kinds of errors, sampling errors in it. So we switched to Gen tilde objects with gate, which worked perfectly. So maybe just a word of advice, that's a really good way to go when you're doing the signal processing stuff, because the Gen tilde objects are basically in C. They're C subroutines, so they're very efficient and accurate. Those control different kinds of oscillators. So then we have, it's just basic, you know, sound synthesis, 1960s, 70s style. And then that goes to some sort of mixer output. So again, I've mentioned this a little bit, but we kind of developed a 4-state quantum synthesizer here. So what that means is you can have wave selection, you have frequency selections, and then we applied some envelopes so that we could differentiate our sounds from each other, and then phase modulation on to kind of make audible the quantum flux, and then some sort of dry-wet mixing between the raw signals and the state signals. In the case of the quantum delay effect, we have bad follower. That is the example I just showed you from the Ableton Live interface, and that's really, I think, an intriguing direction is sort of these effects you could maybe only or very easily generate in a quantum system that become harder to do in or more elaborate in a classical system. This is a really exciting direction that I feel like we just started to scratch the surface on. And so one of this is using the fridges as a synthesizer. So these were projects coming out of Luke's work. Luke was able, he had a very good digital analog converter FPGA on his fridge. And so we were basically doing ground state biasing or excited state biasing. So basically a forced operation that you take a measurement. If it's in the right position, you leave it. If it's not, you flip it. And so that's actually one way that they use to kind of set up some of their experiments. They get the qubits in a particular configuration and they run their experiment. But we also pushed the boundaries a little bit with this and created kind of time-based functions. So transitions from excited state to ground state or vice versa, or sweeps. And finally, he referred to this as a feedback sweep, but a type of like pattern generator where basically you can start to create low frequency oscillations or patterns in that information. So to do the performance, this happened in 2019 for the Arts and Ideas Festival. We basically queried some live data, so to speak, or live data from the fridges for Luke and Carle. We prepared that into the set, and then we performed the set. And then, I did the mixing as well as I had kind of data from previous that we could mix into the show. And that was performed twice, and we broadcast the last performance or the first performance live.
The first performance was broadcasted live onto local radio, WPKN, and then we recorded all the sounds to release an album that we're working on, and it's coming soon, so we should have something early 2022. And so I think we have an extract of the music.
Which one is that?
Just before that. Okay. Yeah, we have like a 40 seconds. And so what I really like about this is that we took all the very dry jump of states, like you usually hear beeps up and downs and different frequency, but like Spencer and Kyle and Luke really turned that into like a very nice performance. And then we had the audience that came in this lovely jazz studio. We created some like really like a very nice mood with like lightings, and so we're very excited to present this later on tonight at the demonstration. We recorded yesterday a live performance of a new set that we did next to the fridge. We actually took the data from, so it's a fun thing. So it'll be tonight at 7:10 p.m. So we'll hopefully we'll see you there.
Yeah, I wanted to wrap up one thing on this, which is that ultimately I think the goal was to like create a musical experience with these systems. I think it's an important evaluation to say, okay, we're going to work with these devices, but like, what is it that we're going to generate with them? And I felt like it was really gratifying to watch the scientists that we were working with grow and change and kind of like really get into the project. And also I kind of stayed out of the way artistically from what they were doing. If they wanted to contribute something or add something to the performance, we included it as much as possible. Yeah. Well, anyway, thank you. If you have any questions, I think we have.
Yeah, we have about 5 minutes.
5 minutes or so. Yeah, 4 minutes.
Thank you, guys. That was fantastic. I'm very interested in this idea of using actual quantum devices as musical instruments. I think it's something that I've been longing to do for a long time, and it's great to see that this is happening. Because it's not all laboratories that will give access to artists and musicians to actually handle these machines. I think I take my hat off to you guys. Those fantastic initiative.
But also the challenge of that thing is that these machines are really, really complex, cost a lot of money, and so it's really difficult for anybody to like go in. And so you really need to partner with actual quantum researchers that know how to do, because all of these quantum computer prototypes are built like from scratch, handcrafted, and so you really need to, like, I think to have any success on this kind of project combination, you really need a partnership, because I don't think the scientists can do a wonderful performance like Spencer did, but I don't think the artists can come in and like run the fridge on their own. And so,
I will say that, like, you know, we spent probably an unbelievably large amount of our time just getting to know each other, you know, like, and actually coming up with a common vocabulary, you know, a common way that we could discuss things. So, you know, I think you probably have felt this in your own, Eduardo, you've worked on so many different areas and fields, so this is probably very relatable, but we all have different ways of talking about things as simple as signals and you know, states even. And so this ended up being a lot of our time was saying, well, what exactly do you mean?
Exactly. I mean, the words that comes to mind is quantize. In music is one thing, and in quantum computing, of course, is another thing. And you know, if you write quantize in a paper, then you have to put the footnote explaining, well, in computing it means this, and music it means that. So it's a matter of translating languages, you know, and making the other side, let's say, understand the concepts and so on. So I think this is a very fruitful collaboration that you are developing there. Now let me check if there are any pressing questions on the chat. I cannot see any. I think everybody probably got what you're saying.
We were very clear. We were very clear.
Very clear. Very cool. We could not hear all the examples you played there very clearly, but we will have a concert later on. So
yes, so there will be about 20 minutes of performance, and we'll make sure that the audio is properly shared.
Exactly. Okay. So for everyone that's listening, so don't forget to join us later on at 6:30 in UK time for performance, and we'll be also presenting other compositions that were made using quantum computing technology.